Okay, so today's lesson is going to be 2 days. Goodbye, book. We'll probably do about half of it today, so you should be able to get through the surface area portion of the homework tonight. And then tomorrow we'll talk about parametric surfaces and how that ties into the whole surface area concept. So here's what we're talking about. So up here we have some function, z equals f of x, y. Down here we have some region R. And if we go upwards to the surface, what we're going to be interested in this section is figuring out what area on the surface corresponds to the region below in the xy plane. Okay? So that's the question is, what is the surface area in that blue section up there? Okay, and the idea that we're going to use is going to look very similar. We're going to subdivide R into rectangles. And now what I'll do is take one of these, and I'm going to go ahead and find where that little section is. So this little section in the region R maps to this little patch, which we're going to call a curvilinear patch, which, if I drew again, it's not going to be a rectangle. I mean, here in the xy plane it's a rectangle, but you guys understand, depending on how the surface, what the shape of the surface is, this may be a rectangle, it may be curved. You know, there's a lot of different options for it. Okay, so now what we're going to do is define some things here. Let's call this corner point P. And let's say P has coordinates. Let's go ahead and call it P sub k. So then x sub k, y sub k would be the coordinates for x and y, and then the z coordinate would be found by plugging in x sub k and y sub k into your function for z. Now we're going to let the area of the patch be delta s sub k for surface area. Now, down here, this is a rectangle, and we're going to have delta x sub k be this width in the x direction, and then delta y sub k be the width in the y direction. So then the area for this little guy down here will be delta a sub k. Okay, so that's kind of, I think that's all we need as far as figuring out what formula we can use to find the surface area. Okay, so we can't directly find the area of every single one of these little patches up here, mostly because they're not parallelograms or they're not rectangles. So the idea is that we're going to, let's write this down. So define area, we'll take a look at the patch, but instead what we'll do is find a little tangent plane . So we'll use a tangent plane to approximate the area. Okay. So again, here's P sub k. Now, one way that we have to find area of rectangles or parallelograms is to actually use vectors. So what we're going to do is call these two adjacent sides, we're going to label as vectors Q sub k and R sub k.
Is the plane tangent to the point K?
Yeah, that's the point of tangency, yes.
Okay.
Okay, we're going to call this little tangent plane sigma sub k. So this is the portion of the tangent plane over the patch. So we got a lot of stuff going on here. Now, the area if we just focus now on finding the area for sigma sub k, then we can use some formulas that hopefully are familiar, which is that if we take the magnitude of the cross product of the two vectors, that should give us the area of one of these parallelograms. Okay, so the idea is going to be the same as before. Eventually we're going to make these patches as tiny as possible. We're going to have an infinite sum of these tiny little parallelograms, and it's going to become some sort of integral. Okay, the question is, what the heck is R sub k and Q sub k going to look like? So let's find that out. R sub k, if we're looking at the vector that's parallel to the y-axis, there is no change in x, so the x component would be 0. Does that make sense? The y component is going to be delta y sub k. And now the question is, I mean, my picture doesn't do it justice, but this could be angled slightly so that there is a change in height there. Does that make sense, depending on how the tangent plane is oriented? Okay, so we're going to have some kind of z component. What's a good way to approximate that change?
Partial y partial z.
Close.
This is the L approximation.
So the differential is partial x. We can do this. So the change in z is approximately partial x times delta x plus partial y times delta y. But there is no change in x. Does that make sense? So then the approximate change in z, partial y I'm going to write as partial y of x sub k, y sub k, and then delta y sub k is your delta y.
Why are we doing two tangent vectors? Like, haven't we always just done one to figure out a tangent plane? Like the gradient, or what do we do?
Well, no, because if we need a plane, we need two vectors. You can't just have one. We're not finding the equation of the plane. We're actually trying to find the area of a portion of the plane. Right? So think about what we did not last chapter, in chapter 11 when we had area of a rectangle or a parallelogram. If I said if I gave you 4 points A, B, C, D, and I said find the area of the parallelogram using vectors, you would have to make two vectors and find the cross product and do the magnitude of it. So that's what we're doing here. It's the same thing. Okay. Everyone okay with the notation here? I see a lot of discussion. I don't know if people are confused or... You can't draw the Q? Okay. All right, if you guys get what's going on, you should be able to tell me what Q sub k is going to be. Now we're talking about this vector here.
X delta X delta K. There's like 6 of us.
Okay.
I got it.
So let's find the magnitude. Yay. So the magnitude is just the cross product. So we'll do I, J, K in the first row. And to make the notation a little less writing, I'm going to stick with 0, stick with delta y sub k, but this I'm going to just call partial z partial y, because that's the same thing. And we're going to assume that we're going to plug in x sub k, y sub k, so I'm not going to write that. And then here I'll do the same kind of thing, delta x sub k, 0, partial z partial x, delta x sub k. So actually, we're not finding the magnitude yet, we're just finding the cross product. Sorry, I shouldn't have done that yet. This cross product is going to be partial z, partial x, delta x sub k, delta y sub k. That's it for the first component. You guys see how I'm getting that, right? The second component, this term cancels out, and then we subtract this term, but do the opposite. So we're going to get partial z, partial y, delta x sub k, delta y sub k. And now the z component, we have 0 minus delta x sub k, delta y sub k. So that's the last component of this vector. Am I sure?
Is this simplified?
Yeah. Okay. Now let's find the magnitude. So the magnitude is going to be the square root of the sum of the squares. So partial z partial x squared, delta x sub k squared, delta y sub k squared, plus partial z partial y squared, delta x sub k squared, delta y sub k squared, plus delta x sub k squared, delta y sub k squared. Well, we have something in common to all these terms. Each one of these three terms has a delta x sub k squared, delta y sub k squared, yes? So I'm going to factor it out, take the square root. I'm going to get delta x sub k, delta y sub k, times the square root of partial z partial x squared, partial z partial y squared, plus 1. What is this, though?
dx dt.
It'll become dx dy, yes. This is delta a sub k still. Okay, so that's what one of these little patches right here, that's what the area would be. Now,
Not for the next little patch.
what's that?
Not for the next little patch.
Well, we just do a sum. So we take the limit. So the actual surface area will be the limit as n goes to infinity from k equals 1 to n of all of these little areas which then gives us the surface area formula. This is going to be a double integral because we have an area out here of partial z partial x squared plus partial z partial y squared plus 1 dA. So here's one of the first formulas in this section that you need to know. And maybe that derivation will be on the exam. Who knows? That'd be a good question. Prove that the formula for the surface area is this. Okay. Any questions on how we got this nice formula? Well, it is pretty nice. I mean,
really not that nice.
okay, well,
I don't know.
Are you saying what's nice compared to the rest of it?
Let's do an example.
okay, let's do an example, shall we?
And I'll see if it's complicated. It really doesn't matter if I think it's complicated or not. But
You should just be amazed that we're doing some really interesting and difficult things here.
I am. We get to confuse people in our physics class.
Find the surface area of the part of the surface z equals x squared plus y squared that lies under z equals 9. Again, I like to sketch, if I can, what's going on. What shape is x squared plus y squared?
A cylinder.
It's a paraboloid.
It's a paraboloid.
Now, their cross sections are circles. Maybe that's what you were thinking of. Here's z equals 9 right up here. So if we're looking for the surface area under z equals 9, then we're essentially finding the area that wraps around the paraboloid. So then the region R would just be the shadow from here to the xy plane. So this is R down here. Everyone kind of see the sketch here? So let's find the surface area. We know surface area is the double integral I'll deal with the region later. First I do partial x, which is 2x, and I'm going to square that, so 4x squared plus partial z partial y is 2y. You square it, you get 4y squared plus 1 dA. Okay, so here's where you can make a choice. We could set up a rectangular double integral, but I mean, I see this nice circle down here. That's probably an indication I shouldn't. So let's stick with polar. What is this circle down here? Good. So if I integrate over this polar region, r would go from 0 to 3. Since we're going all the way around, theta is 0 to 2 pi. And let's switch this out. What's 4x squared plus 4y squared going to be? 4r squared plus 1. And now dA is r dr d theta. Why don't you guys finish this? This is what I'm getting for the answer. It's kind of hard to see for you guys. Something equivalent to it, maybe. Pi over 6 times 37 to the 3 halves minus 1. Any questions on that? Okay, we can end here, but here's something I do want you guys to write down because I know that some of you haven't checked the trig substitution supplement. I recommend that you really look through that if you don't know or if you haven't done too many of those.
I'm not sure how to read the table.
But I can tell you, here are some helpful ones. Sorry. Some helpful trig substitutions whenever you see square roots that look like some constant minus x squared or some constant plus x squared, or maybe these are switched, x squared minus a squared. Again, the idea that when you do a trig substitution for something like this is that you want to turn this square root into just a single trig function that's squared. Okay, so right here, we did one like this earlier in our class. I forget what day it was, but if you just do a and either cosine or sine, but I usually use sine, this square root becomes a squared minus a squared sine squared. Does that make sense? You can pull out the a squared. You got 1 minus sine squared. You get the square root of cosine squared, which is cosine, and then life is good. Okay? Here, we want to find a trig identity where you add, so maybe something like x equals a tangent theta, because now you can pull out the a squared, and then you get the identity that 1 plus tangent squared is what? Secant squared, and then you get secant. Okay?
Can you just plug in whatever you want for x?
Well,
Like what?
it's based off of what this constant is here. So it's not just an arbitrary, you know.
Yeah.
Oh, yeah. The bounds, read through the you'd have to change the bounds of integration. Like if you do a substitution like this, you don't just leave the bounds and then, I mean, you could leave them and then switch it back to x's at the end after you integrate, but I think it's easier to just, like if x is from 0 to 1, let's say, you set x to 0, x to 1, and then find out what theta has to be based off of that. Does that make sense? Here,
No, what about the y? What do you do for the y bound?
well, you treat it as a single variable problem. So it's one or the other. You can use a secant theta. Okay, so these are some helpful substitutions. If you're not sure how to do them, please read through the supplement. It's not something from a textbook I pulled. I actually typed it up and explained it. Okay, so take some time and read through it.